All right, so one more law here, and it's called Dalton's law of partial pressure. So partial pressure is relevant when you have a mixture. So say in air, we have a mixture of nitrogen that's about, I don't know, 78% or so. Oxygen is somewhere around, about 18 or 20%. We'll say 20. And then there's also CO2, somewhere around 1%, some argon, a little less than that. It keeps going. You have trace elements. So this is a mixture of gases. The total pressure, which we've referred to before as barometric pressure, like we measured in lab the other day. So the total pressure of air is equal to the pressure of each gas added up. So if I know the pressure of nitrogen, pressure of oxygen, pressure of CO2, all these different gases, and I add them up, then I get the total pressure. Okay, so another example of this is whenever we are collecting a gas over water, kind of like we did with that green trough when we generated oxygen in 111. In that situation, the total pressure is due to the gas I generated, say O2 in this case, plus the water molecules that are present in the sample as well. Air is never dry. Air and other gases always has a little bit of water vapor mixed in, which we kind of need. If the air was really dry, your skin would get super dry and your eyeballs would hurt and all these things. So these values are tabulated, which means they're available all over the place. We have a giant book in the lab that has this. But at any given temperature, you can find the pressure of the water in the air. And so if I can measure barometric pressure, and I look up, based on temperature, the pressure of the water vapor, that means I can calculate the pressure of O2. So let's say, for instance, I have an experiment where the barometric pressure is 1.14 atmospheres. So that means the total pressure. Barometric pressure means total pressure. So I could even just define that. P total equals 1.14 atmospheres. And then I look up. So I need to have the temperature to look up the vapor pressure of water. So it's room temperature today for this example. And you can search online for this. It's a little iffy. Sometimes the websites aren't very reliable for this kind of thing, or you can look it up in the text that we have in the lab and also my office. So this text that I have says that the vapor pressure at 20 degrees Celsius and roughly 1 atmosphere of pressure is 17 millimeters of mercury. Actually, it's 17.5. Okay, now I'm going to have to convert that because the units of pressure have to be the same. So I put in 17.5 divided by 760, and we find that the pressure of the water vapor is pretty small. So the total pressure equals the pressure of the gas that I was making, say oxygen, plus the pressure of the water. So here we know that the total pressure was 1.14 atmospheres. I don't know the pressure of my gas. That's usually what we're trying to find. I do know the pressure of the water. So to solve this, I'm just going to subtract from both sides. Oops. So the actual pressure of the gas that I made is going to be 1.12 atmospheres. Not quite as much as I thought, but still pretty close. Okay, so this is how you can use Dalton's law of partial pressures in the laboratory.